Alright, so in this video, I'm gonna be explaining this article, characterizing and avoiding negative transfer. Because we don't want to transfer everything. We don't want to transfer even the negative part, because when your transfer is successful, it's positive, but when you're transferring something like the domain specific features, then then it's a negative transfer, which is a bad thing, because you are transferring something that is not in it is the semantic intrinsic nature of that concept. So this paper from Carnegie Mellon University in 2019 is very important. When labeled data is scarce for a specific target task, transfer learning often offers an effective solution by utilizing data from a related source task. However, when transferring knowledge from a less related source, it may inversely hurt the target performance, a phenomenon known as negative transfer. Despite its pervasiveness, negative transfer is usually described in an informal manner, lacking rigorous. For example, in some paper, they noticed that if they transfer the background color, for example, we have this background color for cat in the source domain, and in the target domain we have the same background color of dog. If we just use these domain specific features, which is about just the color, and transfer for the second domain, which is a target domain, for example, then we think that this is a cat as well. So we want to distinguish them. We want to, for example, if it is our feature, some of them are feature invariant, domain invariant. Let's call it domain invariant features, and domain specific. In domain adaptation, we want to get rid of this one. We don't want to use this. Only this part is important, domain invariant, because this part produces spurious things, and it's a negative transfer if you want to use that. So we just prune it, we just remove that part. This paper proposes a formal definition of negative transfer and analyzes three important aspects thereof. Stemming from this analysis, a novel technique is proposed to circumvent negative transfer by filtering out unrelated source data. So based on adversarial network, the technique is highly generic and can be applied to a wide range of transfer learning algorithms. The proposed approach is evaluated on 6 state-of-the-art deep transfer methods via experiments and 4 benchmark datasets with varying levels of difficulty. Empirically, the proposed method consistently improves the performance of all baseline methods and largely avoids negative transfer, even when the source data is degenerate. So we have this notation to say that this is a joint distribution. This is the of source, and this is joint distribution of target. We have transfer learning. So we want to design an algorithm which takes both the source and target as input and outputs a better hypothesis, H. So H is our hypothesis, and this is loss. And so this is the standard expected risk that you should know in elementary machine learning. So L is just specific task loss. To make the setting meaningful, it is assumed that number of S is much bigger than number of L. So number of L is the target, number of source is much bigger than number of target. The number of source samples, I mean. The notion of negative transfer lacks a rigorous definition. So negative transfer should be defined with respect to the algorithm. Specifically, the informal information above does not specify what the negative impact is compared with. For example, it will be misleading to only compare with the best possible algorithm only using the target data. For example, defining the negative transfer as this one, that are the risk of your target is bigger than minimum of this among all algorithms. This is our notation, an algorithm A. So among all algorithms, if the risk of the target is bigger, then we have defined the negative transfer. But this is misleading because the increase in risk may not come from using the source domain data, but the difference in algorithms. Therefore, to study negative transfer, one should focus on a specific algorithm at a time and compare its performance without the source domain data. Hence, we define the negative transfer condition like this. So one algorithm at a time. We can compare that if the risk of that is greater. So for convenience, we also define negative transfer as a quantifiable measure of negative transfer. And we say that negative transfer occurs if the negative transfer gap is positive and vice versa. Divergence between the joint distributions is the route to negative transfer. As negative transfer is algorithm specific, it is natural to ask a question that whether there exists a transfer learning algorithm that can always improve the expected risk compared to its target domain only baseline. It turned out this depends on the divergence between P sub S and P sub T. As an extreme example, assume that the probability of source and target is the same, and probability of source of label given X is uniform for each X. In the case, there is no meaningful knowledge in P sub S of X of Y at all. Here, hence, drawing S from this probability distribution will almost surely harm the estimation of probability of target unless probability of target of Y given X is uniform. So in practice, we usually deal with the case where there exists systematic similarity between the two joint distributions of source and the target. Then an ideal transfer would figure out and take advantage of similar parts, leading to improved performance. However, if an algorithm fails to discard the divergent part and instead rely on it, one can expect negative transfer to happen. Thus, regardless of an algorithm choice, the distribution shift is the actual route to negative transfer. Negative transfer largely depends on the size of the labeled target data. While the previous discussion focused on the distribution level, an overlooked factor of negative transfer is the size of the labeled target data, which has a mixed effect. on one hand, for the same algorithm and distribution divergence, NTC depends on how well the algorithm can do using target data alone. For example, the right-hand side of equation 3, this part, so in zero-shot transfer learning, where there is no labeled target data, only using unlabeled target data would result in a weak random model. Thus, NTC is unlikely to be satisfied. When labeled target data is available, a better target-only baseline can be obtained using semi-supervised learning methods, and so negative transfer is relatively more likely to occur. At the other end of the spectrum, if there is an abundance of labeled target data, then transferring from an even slightly different source domain could hurt the generalization. This shows the negative transfer is relative. This part is very interesting. You can read it several times. You understand it's very interesting. So on the other hand, the amount of labeled target data has a direct effect on the feasibility and reliability of discovering shared regularity between the joint distributions. As discussed above, the key component of a transfer learning algorithm is to discover the similarity between the source joint probability and the target joint probability. When labeled target data is not available, one has to resort to similarity between the marginals. At least we have the marginals, which though has a theoretical limitation. Do you know what? Because how can you know, for example, that background color with cat is different from background color with dog? They are from different classes. If you don't know the label of that this is cat, this is dog. If you know for the source, but if you don't know the label of the target, because in unsupervised setting of domain adaptation, we don't have access to this for training. So that's why it says that it has theoretical limitation. In contrast, if one has a considerable number of samples, the problem would be manageable. Therefore, an ideal transfer learning algorithm may be able to utilize labeled target data to mitigate the negative impact of unrelated source information. So the key to achieving successful transfer and avoiding negative effects is to discover and exploit shared underlying structures between P source and P target. In practice, there are many possible regularities one may take advantage of. To motivate our proposed method, we first review the important line of work and show how the observation helps to identify the limitation. So to find a feature extractor, like a backbone, because we always need this to fool the discriminator if you are working on the adversarial paradigm. So to find such a feature extractor, a representation solution is a domain adversarial, which exploits a generative adversarial network to train feature extractor F. This one is F, such that the feature distribution of P of F and P of F of xt cannot be distinguished by the discriminator. So P is your probability. Because we are a discriminator of generator. the generator tries to fool the discriminator. C of f and d of f. So these are we have two losses here that I will go through that. But CLF is just the supervised classification loss. So, and adversarial is the standard GAN. This one is just the adversarial GAN. I mean, discriminator of the generator. So you know this part. And this part is just the classification because it's a supervised task. The classification is a supervised task. We have the labeled data of source domain, so why not classify? So we have this classifier because it has we have a loss for that, and we have the discriminator, so we have an adversarial to design this f such that it fools this discriminator. So everything is standard here. But the discriminator gate, this ratio is very important. I've seen several papers. The limitation of DANN, I mean domain adversarial neural network, the limitation of that comes from the unnecessary assumption that all source samples are equally useful. You know, even in active learning, we have some uncertainty to show to the annotator that you should annotate this sample because the machine suggests that. And we get that uncertainty from probability of your label given X. So with the same analogy, with the same understanding, you can say that even the value of that, you don't need argmax of that. Even the value of the probability is saying a lot of things about how confident you are, how uncertain your estimation is. To derive an approximate weight, notice that the standard supervised learning is this. But the density ratio naturally acts as an important weight for the source data. So we say when we sample from the target distribution, it's like sampling from the source, but we add this interesting weighted factor, probability of T divided by probability of S. It shows how much important the probability of the target with respect to S is. Hence, the problem reduces to the classic problem of density ratio estimation. Density ratio estimation, at any point, optimal discriminator is given by this. We know that theoretically. So that's why we say probability of T divided by probability of S is equal to D. So it just rewrite this, becomes this. So in our implementation, to save model parameters, we reuse the feature extractor to obtain feature of X and instantiate D as D of F. So we modify this 6. We just modify this classification because we are getting from target and from S. So we modify that like this. Now it becomes D over 1 minus D. I mean this stock gradient of D over 1 minus D. And this is the W, the weight that you need to multiply. It's not like before. And then we also augment the adversarial law by incorporating terms of matching the joint distribution. Because nil here is just a dummy label which does not provide any label information, and it is included to enable the discriminator being used as both the marginal discriminator and a joint discriminator. So we combine all of them. We arrive